Okay, so what do we need to be able to formulate an analysis in a decision tree form? At our decision nodes, as I said before, we're going to need mutually exclusive decisions. And at our event nodes, okay, we're going to need mutually exclusive scenarios. Either we're awarded the contract or we're not, that type of thing. We've got to consider all possible scenarios. And of course, if we're considering all possible scenarios, the sum of the probabilities for each scenario has to add up to 100% or 1, okay? And across our stages along the time axis here, time or stage axis here, the probabilities need to be independent. So let's see how that looks here. Okay, here's another, this is a different simple analysis here, but what I want to show you here is that for any decision tree, as we move along the time or stage axis, the probabilities need to be independent. And so what that means in this case, we're looking in this case at whether or not we should buy a high yield bond. We've got a 3.5% chance that there's going to be a market crash while we own this bond, and a 26.52% chance that, that we have a 73.5% chance that we won't have a market crash while we're holding this bond, and we have a 26.5% percent chance that there might be a market crash. Then when we go on in time, we're saying if the market is okay, we have about a 79% chance that the company who issued the bond doesn't default, but that means a 21% chance roughly that the company will default. And so what we mean here by probabilities independent is that these are independent, okay? Okay, and what we mean by our scenarios being mutually exclusive on the y-axis here is any time that we have an event node, only mutually exclusive things can happen. Either the market's going to be okay or it's going to crash. We're going to consider them both, and the probabilities for all of them have to add up to 100%. Same thing here. Either the company issuing the bond is going to default or they're not. Here's no default and here's default. So they have to be mutually exclusive scenarios, and they have to, of course, we have to consider everything, so the probabilities have to add up to 100%. Few more definitions we're going to need to know to make this happen, okay? The project expected value, we're going to call EVP. I've been throwing that around without defining it carefully. This is the expected value of the net cash flows when moving through the tree, considering only each optimal choice, each recommended choice through the tree, okay? And what's an optimal choice at a branch node? That's going to be, as I said, the choice or the branch with the highest expected value for the project. Okay, so how do we go ahead and solve a decision tree problem? It's always good to, whenever you're doing any real-world financial project, define a risk-reward policy for this project. And I'll talk about that a little more later when we get into our example. Then you want to build, one way or another, a futures table. I've got a certain way of doing it, but all it really is just thinking about what could happen during the project, what the probabilities are, what all the decisions are that we have to make, because that's what you're going to have to put in as input to your decision tree, okay? Then we're going to build a decision tree using that futures table data, and then we're going to solve for all of our unknowns, and we're going to start doing this without consideration of time value. And that's the equivalent to, in our mathematics of money and the chapter, my review chapter for you on this, that would be considering that opportunity cost of capital is equal to 0. That's the way it works out. That's the same thing, that's equivalent to, and gives us the same answer as just saying we're not considering time value at all, okay? Next, we're going to go back, so we'll solve that whole thing with we're going to solve this whole thing without considering the time value. And then next, that's going to help us debug technically the decision tree, make sure everything looks good while we're keeping it simple, right? And once we feel like it's debugged, it's working well, all that stuff, we're going to go back and consider the tree with time value, okay? And to do that, what are we going to have to do? We have cash flows in the tree that are going to happen a year from now, 2 years from now. We're going to have to take the present value of all of those. And once we take the present value of all of our cash flows, discount them back to their equivalent at t equals 0 or right now, that's going to give us, instead of what we call the expected value of the project, that's going to give us the expected net present value of the project, which is awesome. That's what we want in a time value world. And of course, to do this, to discount back, we're going to need to know our opportunity cost of capital. Next, we're going to apply our risk-reward policy, and typically that's going to have a target that we're shooting for and a downside limit. So we say we want to maximize the expected value of this project, but we want to make sure that no matter what happens, we don't lose more than $50 million. That would be our downside criteria, that type of thing. So we apply both of those, and then we can make our decision. Do we want to go ahead with this, yes or no? And then finally, always good with something like this to consider the limitations of the model. The fancier we get with financial models, the more simplifying assumptions we have to make, and it's very important that we're aware of what those assumptions are, because that tells us where the model may not apply, where we may not use this model, or where, if we're not careful, we may erroneously try to use this model. So we'll look at that too in the context of an example. Okay, and here again I have the last of my self-serving, shameless, and gratuitous plugs. Helpful material for all of my modules, including this module.